recognizing that and trying to embrace that is something that I think is part of the future and really important. And stream restoration is part of that conversation. Welcome everybody that's popping in. Good to hear lots of things coming in. So let's see if gotta get on the right slide, I think, to move it forward. There we go. And so my talk is going to kind of jump a little bit back and forth, but in general, starting with kind of where the location in a watershed, from upland to floodplain to in-stream, which includes the restoration processes, hyperheic zone, and then impact. So water quantity and flooding, water quality, and impacts to the habitat within the stream, or within the entire watershed, and kind of talking about processes. Once again, this is about a presentation I gave to floodplain managers. So there's some things related to stormwater management that they really don't have a lot of background on, and then talking about some applications in specific locations. So starting off with stormwater, looking at flooding and water quantity, water quality, which flooding obviously is something that the floodplain managers think about a lot. Water quality is something that they don't think about a lot, and to some of them is a little bit scary because they're afraid that it will take away from the focus that they have on floodplain management and prevention. And so just wanted to partially talk about the tie between them. And when I was pulling together the presentation, I wanted to start talking about the hydrologic cycle, but man, it's hard to find a hydrologic cycle that includes in-stream processes and the floodplain as part of their overall picture. And so I actually searched for this picture for quite a bit, but looking at the different parts of the hydrologic cycle, including the floodplain and groundwater surface water interactions within the stream. And you can even see that, in the downstream of that, it appears that the stream is somewhat incised. So there's a lot of things that on this particular hydrologic cycle image that really plays into this nexus of stormwater and floodplain management and in-stream management. And I think most on here have probably seen this image, but discussions of impacts, land use impacts on the water cycle, where depending on the percent impervious surface, these are some EPA images. In this particular instance, you can get 5 or 6 more times more runoff when you get lots more impervious surface. That isn't news to a lot of folks here. Specifically, I was talking in Oklahoma, and we have a book called the Water Atlas of Oklahoma that talks about average parts of each part of the water cycle. And Oklahoma, a lot of people think about Oklahoma as just straight prairie, but Oklahoma is really diverse. It has 13 different ecoregions, going from the Panhandle, where there's 15 inches of rain, to southeast Oklahoma, where there's 65 inches of rain average per year. There's actually native alligators in southeast Oklahoma, and that's all in the foothills of the Ozarks. And so the natural system down in southeast Oklahoma may be 1/3 runoff, lots of rock. Like I said, foothills of the Ozarks, lots of rainfall. Central Oklahoma, which is where Oklahoma County is, Oklahoma City, it's about 15% runoff, a lot of evapotranspiration. And then you get out to the Panhandle, not as much rainfall, but the rain that does fall, it's relatively sandy. It'll go into the shallow subsurface, but then 97% of that water actually evapotranspirates, and there's only 2% runoff. And so impervious surfaces in an area where there's naturally only a 2% runoff, and you change it up to 60% runoff, man, that's going to make a huge impact on our water quality, on our streams, compared to what is there. So I wanted to start having that conversation and have them think about from east to west, even just the different things that we're dealing with, and how that's so important. And as I mentioned, this was floodplain managers. Some of them wear more than one hat and they know what stormwater management is. some of them, they're emergency managers or other areas. And so on the background, just starting to talk about traditional stormwater management with pipes, channels, ponds, things that move the water off as quickly as possible. And in this group, we know that that's causing impacts of degradation of the stream and the floodplain downstream potentially, and to the habitat. And talking to them how a detention pond works, where we're trying to get the pre-development peak flow rate equal to the post-development peak flow rate. And a lot of places in Oklahoma, the ponds may be sized for a particular development, but then there's another development comes in 5 years later upstream, and that pond is now undersized for that entire area, especially in some of the smaller communities where there's less thought about connection and integration of the management. And there's also a water quality component to detention ponds. The folks in this room are thinking about detention ponds solely from a floodplain management and a flood management standpoint. So just kind of bringing some of those numbers in there from our nutrients, sediment, heavy metals, some of the things that are causing a lot of impaired streams in Oklahoma. Next, we move into low impact development, sometimes called green stormwater infrastructure, or a lot of different types of things. With the primary goal of water quality improvement. Usually when you design these, you're trying to intercept something that's often called the stormwater volume, at least in Oklahoma and a lot of the areas around here. That's often between the 85th and 90th percentile storm, somewhere around and intercepting the first inch. That's not going to do a lot for your flood. And I just went through a little exercise utilizing the rational method. If you put some kind of LID structure like bioretention in the corner of an impervious area, depending on how big that bioretention cell is, if it's 5% of the area, it's that orange area. If it's 10%, it's the yellow, and hopefully y'all can see those colors. If it's 15%, it's the purple. But depending on what the infiltration rate of the soil is, you're really only reducing the peak by less than 10% with traditional bioretention design. And that's a question that I get a lot from folks that are in the flood area and really in Oklahoma, because flooding is a much more in the news and on the mind issue than water quality. And so when you're talking to them about spending money on stormwater management, such as green infrastructure, they ask about the flood reduction. And, as traditionally designed, you can't do that. But this is just, once again, an exercise on a 4-hour storm, type 2, which is in Oklahoma with 100-year. In Tulsa, a little over 5 inches. If you design it right, so that loading ratio is what we were just talking about, the percent of the drain of the LID practice compared to what's draining in, and designing it. DC is design criteria. So if you design it big enough, you can make it so that it will address and get you down to the peak flow that you'll see pre-development in that area. Those last two with a loading ratio of 20%, and designing for 3.6 inches, or a loading ratio of 0.56, which isn't necessarily realistic because it's greater than half of the area. You can do it with 2 inches, but there we're able to reduce the flow. And we actually have a over $4 million installation that I helped design going in Oklahoma City that is doing just that. And I think we'll talk about that a little. No, I won't talk about that specific one, but here's a similar exercise that we did in Tulsa in the Pearl District. One of my former master students, Andrea Tavera, did this looking at the Pearl District. It's an area in Tulsa that floods a lot. It's just to the east of downtown, older part of the city, where we went and we used a model called info drainage, modeled it, modeled the troubled areas, did some optimization, trying to design for water quality, but also that hits on water quantity. So we're reducing the flow, bioretention, and pervious concrete in that area, looking at 3 different different areas. And with green infrastructure, we can reduce that flood flow around 75% at the 3 areas, and reduce that 100-year storm to less than the 1-year storm for those drainage areas. And that's something that's pretty attractive in these areas where it's all built out, older neighborhoods, and buying out areas to build detention ponds is not necessarily politically popular. And so if they can do some other things, that's really great. At the same time, we're really helping the water quality with sediment, nitrogen, and phosphorus reduction in those areas. And here's the cost estimates for what we had proposed, about 1.4 million. The cost of buying out lots and building ponds is greater than this. This obviously is just the capital cost, not the maintenance cost, but still it's a pretty cost-effective solution, and something that even in Tulsa we're continuing to have conversations with them about that. So that's the upstream part of the drainage. And then moving into the floodplain, once again, the audience that I was talking to for this presentation was Floodplain Managers. There's this really nice document out there, if y'all haven't seen it before, 9 ways to start connecting stormwater and floodplain management, that has some pretty similar type of topics. But at the National Stream Restoration Conference, David connected me with Will Wilhelm, and I borrowed a couple of his slides because I thought it was so pertinent. I don't know if anybody got a chance to see his presentation, but he was talking about an area that he was looking at, 1.2 miles of stream with an 80-acre floodplain. And if the floodplain, and this is just an assumption, I talked to him about it afterwards a little bit, if the floodplain stored 3 inches of water, that's 6.5 million gallons stored and treated. And if you're trying to compare that to bioretention basins designed with traditional design criteria, that's 500 to 700 bioretention cells that connected floodplain is performing the same function. And so you can—
It is not.
Pardon? Question? Oh, did somebody say something? Okay.
I think we just had somebody off mute, so just continue.
Okay. Cool. So that is something that it's not been specifically studied. It was just some thought process from Will, and I thought it was really interesting. As a researcher, something that's stuck in my head, and something that I'd love to explore a little bit to see how that comparison plays out. And then this audience, I'm sure, is very familiar with the Los Angeles River that used to look like this concrete, and has been restored over time to be an area where there's habitat, there's recreation, and is once again an example of the interaction between floodplain management and stormwater management. Something that in Oklahoma, where we have lots of channels, lots of concrete for our flood management, something that is definitely something to think about. And as the floodplain managers and stormwater managers are looking to get together, this is a conversation that they can have together. And then finally, I moved into the channel, just talking about floodplains and natural streams on a high level, talking about what streams do at all scales with meandering, and your riffle pool sequences, and how it's trying to decrease energy, with some examples on the Illinois River in eastern Oklahoma that David and a group helped us with, a number of stream bank stabilization restoration areas. But just talking about stream bank, and how, once again, how that interacts with water quality. There's decades of both treated wastewater and chicken litter from Arkansas and eastern Oklahoma that have come into the Illinois River. It's stored in the sediment in those stream banks, and so the more stream bank erosion you have, the more release you have of legacy sediment. There was one study that showed that even if all upstream phosphorus sources ceased just from that sediment, that you'd have phosphorus released for decades because of all the phosphorus that's now stored within those stream banks. So stabilizing that sequesters what's in there. Talked about lanes balance and how that impacts habitat. And finally, moving into the hyperheic zone. So once again, this interaction between stormwater management, floodplain management, in-stream management, and the hyperheic zone for the floodplain managers was definitely new. This is a really in-depth image, so we didn't go really into depth, but just emphasizing the importance of that, of the hyperheic zone in the entire biological system that is in the stream, and the water quality processing that happens within the stream. And then we brought it all together with this slide that's I see utilized a lot of places from the study that was up in the Pacific Northwest that looked at the occurrence of trout and sensitive insects related to impervious surfaces. One of our stormwater managers in Tulsa has actually done this to some extent in the Tulsa area with some local fish. And it's something that I'd like to follow up on some more. And then something that everybody everywhere I think knows about is TMDLs that's in this area, but total maximum daily loads models that partition off pollutant sources to different, or pollutants to different sources, and gives a goal for the stormwater managers and the natural resource managers in the area to try to hit to get, in this case it's like Thunderbird in central Oklahoma off the 303 list for phosphorus, but whatever the pollutant may be. And this is one of the things that once again brings together the importance of in-stream management, whether it be sediment or phosphorus, with the landscape management and the floodplain management. And some of the solutions may be in stream or within the floodplain. Lots of this going on different places in the U.S., but I don't know if it's discussed or intentionally thought about as much in Oklahoma. We did some exercises in the Lake Thunderbird watershed, kind of partitioned off like this to identify where some of the different best management practices would be best utilized, whether it be on the landscape or within the stream or the floodplain. Just did some optimization. I'm going to kind of skip through this for the sake of time, but just found some locations where we could put that and get the best bang for our buck and help out our water resources along the way. The next thing I talked about a little bit was climate change as an exacerbator, and this kind of goes across all parts of the hydrologic cycle, and talked about this project that we're doing in the southern part of Oklahoma, the Red River Basin, basically the southern third of Oklahoma, looking at impacts of climate change and potential water reuse scenarios. That's a climate adaptation strategy that's gaining steam in Oklahoma, but we wanted to look at unintended consequences of that, of basically changing as in floods or changing in low flows, in particular low flows for us, because it would impact stream flow. There's some streams in Oklahoma that if it wasn't for wastewater effluent, there'll be times of the year where it's not flowing at all, where now they are, and so that would kind of change our entire ecosystem and the flow regimes that are going on. And so the flood flows were similar, but when we went to the low flows, flows that are below the historical 30th percentile, which is a simple method that's in the literature and something that we just used as a start for where the environmental flow would be. Historically, by definition, it's 117 days of the 30th percentile. But when you add in climate change, looking at that zero wastewater reuse, so we're not taking any wastewater out of the stream, we go from 117 days to 173 days below the 30th historical 30th percentile, or that environmental flow, and beyond the impact to the fish, that's going to impact the plant community. It's going to impact the stream and the geomorphology of the stream when you do that, because you may have alluvial ephemeral islands and sandbars where now with less water, you're going to get plants established on those and they become permanent islands. Maybe you start to get braided. There's a lot of different things that could happen to the geomorphology related to that. And so just thinking about beyond even just the runoff aspect of it, but the in-stream aspect of what's happening. So kind of my conclusion for the floodplain managers when I was talking about that is, you can't change one part of the hydrologic cycle and management without changing the other. So integrated management is vital for flooding, water quality, in-stream processes, and habitat. TMDLs, we're getting more and more in Oklahoma. So this integrated management is going to be vital for trying to achieve those goals and do what's mandated for our communities. And finally, climate change and water resources management are going to be additional exacerbations to this challenge. It's not in here, but in Oklahoma, we have lots and lots of reservoirs. WPA was very active in Oklahoma in the 40s. And so I heard a stat one time that we have more shoreline in Oklahoma than any state that's not on the ocean. It's because of all of the reservoirs that we have that were primarily for flood control. So management of those along with climate change are going to be really, really important. And so hopefully that's about the right length, I think. And, the intent of this is partially for the content, but a lot of it, especially for this group, is just the discussion that's happening out here in Oklahoma, and I'm sure other places, about integrated management and intentional addressing this from our associations that we have, such as Floodplain Managers, our Stormwater associations, other types of groups. So with that, see if I can figure out how to stop sharing.
Thanks, Jason.
You're welcome.
Yeah, we can open it up for questions and comments.
I would love to hear if there's similar types of conversations going on in other places.
Yeah, I was going to add, thanks, Jason, for that. I was just I'm from Austin, Texas. I often feel like a unicorn at some of those conferences as well. The Floodplain Managers Association probably is very dominated by really kind of the mapping folks and very useful tools, but always got to throw in my 2 cents about impacts and stream management. Let's keep that on the forefront. So I appreciate, I would think after this time, it's pretty integrated into our community, but maybe not as much as could be. And just, the kind of the traditional approaches is to floodplain management, and even just kind of at a very broad level, detention ponds. Well, those squash down the pink, but also can extend the duration of our erosive flows, and just remind folks of that and impacts of levee systems. So I appreciate you kind of just keeping that on the forefront. And I try to do the same thing within our communities as well. So thanks.
Who are you with, Morgan?
I was with the City of Austin Watershed Protection Department, recently retired. And, and that's basically our drainage utility. But we are set up to have an integrated approach. Our primary missions are flood risk reduction, erosion risk reduction, which is primarily where I worked, in the stream management group. And then we have a water quality function. And so when we design our projects for our capital project, we do have a project planning process where all the different stakeholders and experts get to contribute to the project. And that's where, so it's been in our culture of a stormwater utility for quite a while, but not without friction, obviously. So it's a general theme on how we try to manage stormwater within our community, but not as necessarily kind of the same level of energy, say in like Dallas and Houston and other areas. So
Yeah, Austin's definitely more progressive than many of the communities in the region, and someplace that I know a lot of that we look to for first adoption of things and stuff we can use for examples. So thank you for the work you did there.
sure.
Jason, can you hear me? Okay.
Yeah, I can hear you.
Okay. I have a question about kind of what assumptions you made to kind of run the model for trying to find locations for sites for TMDL reduction. What were some of your key assumptions in that model?
So we did it in 2 steps. For our first was more of a broad step, and it was a GIS coverage of overlaps of different things. And so some types of practices may only be practical inside or outside the floodplain. If something is infiltration-based practice, you're not going to do it within the floodplain because you get sediment in there and it clogs up fast, and it's just not a place where you're going to install it. There may be other things that on the in-stream things. The city wanted to just do it on public lands, not on private lands. And so it was kind of we started with kind of a practice by practice approach to overlap and find areas where it would be most likely to succeed. And then from there, I have a custom Excel model that utilizes Solver to look based upon assumptions of removal rate, inputting soil and cost to identify the best bang for the buck for different types of objectives. And you may be looking at minimizing maintenance. You may be looking at a maximum cost that you have in an area. You may be utilizing not utilizing one or more types of practices. And so with that custom spreadsheet, we do it. It's more from a planning standpoint, right? It's so you're not going to have site by site specific things, and you're making assumptions on soil type, that type of stuff. And we combine that with the EPA, the online EPA stormwater model. I'm blanking on it right now, but and so that's what we use for modeling that. And so when we're setting that up, we're looking at an area and running it for 10%, 20%, 30%, all the way up to 100% of impervious area treated by one particular type of practice. And that gives us a regression between water quality and water quantity reductions. And we do that for all the practices that we're doing, tie it together with the cost, and then use that for an optimization. It's more manual than trying to use some of the EPA models out there, but it allows us to have much more control on all the specifics of what we're looking at. So it's a multi-step process, but that's how we got to that point.
Gotcha. So the each treatment was kind of universally applied to the area of concern. Is that, and then that's kind of your analysis, and then you can change catchment size. Is that
well we have one catchment size, one drainage, and so we characterize that drainage, and then we apply each one individually at different percentages of the impervious area being treated. And so then we put that into an optimization model that includes both the results from the stormwater calculator and the results and the cost. And so then for different objectives, whether you're trying to maximize the percent nitrogen reduction or minimize maintenance cost for a certain capital cost or whatever you may be trying to do, we can put our constraints into that solver. And so we're always using one watershed size, but different types of best management practices. That does not allow us to do the in-stream like stream restoration. And so we would do that kind of off to the side, but still have a cost reduction associated with a certain target and just kind of compare that afterwards. And so the in-stream processes and in-stream restoration were not able to be done with EPA stormwater calculator. Does that help?
Yeah, I think that helps. I'm thinking I know Chuck, who's on the line, is looking to kind of we're looking to work with him and help him out in creating some TMDL and rankings of watersheds. Part of it's demonstration wise, but part of it is also just okay, which watersheds are going to get you the most load in. So I was just kind of wondering how you applied the different treatments with your model. So I think that seems pretty close to what my thoughts would have been. I was hoping maybe you had something fancier that was easier, but
there's a few EPA models out there that kind of do the same thing. They're really input intensive. Ours is pretty intensive also, but like I said, we have our fingers on every part of it. So I'm relatively confident that in the results. And once again, it's still a planning tool. So
yeah,
we are making those kind of little bit broader assumptions on removal rates and
cost, those
types of things.
This is Chuck with Louisiana, with the TMDL program. I do find it interesting when you talked about TMDLs and how this all works together. That's something I've been trying to stress, that in our engagement with the local communities. But I guess my question is, how do you relate these kind of a high flow situation to a low flow situation? Most of the TMDLs we've done are related to dissolved oxygen, which is essentially, when we create the TMDL, it's looking at critical conditions, which is high temperature, low flow. But yet the stormwater is a high flow situation. And also, too, I want to add that I've been hearing about this Illinois TMDL for many years through my EPA counterparts.
Yeah, so dissolved oxygen is not necessarily on the forefront of a lot of the TMDLs that we're looking at, except maybe reservoir TMDLs, but then it's still about nutrient movement into the reservoir. And so then it is a high flow situation. So I personally haven't worked, tried to address low flow related things in TMDL. So I don't know if I have a really good answer for that, but that is an interesting question. And that Illinois River TMDL has been in process for a long time. And I think it's kind of out there, but I think it's still being disputed quite a bit. And with all of the lawsuits in that area around chicken litter that have been going on for 20 years and have recently picked up some steam and tried to go into mediation and it was not successful. That's going to continue to be a contentious situation for a long time, I'm afraid.
Thanks.
All right.
I was just going to ask on the TMDL work with the DO, is this in streams then? Is that where you're looking at smaller streams or?
Are you referring to Dave described?
To what you were just discussing with, dissolved oxygen, and is that stream TMDLs or reservoirs or coastal or?
It's stream, and many of them are coastal. Many of them are due to what we believe is improper dissolved oxygen criteria. But it is it's always about dissolved oxygen first. The nutrients is kind of the way our nutrients impairments have been listed in the past is that first there has to be a dissolved oxygen impairment, and then beyond that, there is it's a qualitative, not quantitative, assessment of possibility of nutrients being there. And that's something that's being worked on by other groups in our agency, but that's how the bulk of our TMDLs are dissolved oxygen. We have some nutrients and other things like fecal coliform, lead, stuff like that. Few mercury.
I would say we're mainly bacteria, sediment, and nutrients, and so I don't know if there's I haven't heard of anything in Oklahoma that's primarily focused on dissolved oxygen beyond just receiving reservoirs, and then like I mentioned, hitting on the nutrients. But
We do have a few that are sediment / turbidity.
gotcha.
Okay, yeah, great discussions. Well, thank you, Jason, for the insightful talk. Yeah, so I think Dave, are you gonna take over and talk about the inspiration section?